Okay, let's now talk about the velocity of sound. And what I want to show here is a couple of phenomena that occurs with the velocity of sound. First of all, this velocity or speed of sound is the rate that sound travels. And these rates are affected by two things. The main factors that affect the speed of sound are the medium, that is the material that the sound wave has to travel through, and the temperature. Now, if you sit back and think about that for just a second, it makes sense because sound waves basically have to compress and rarefy molecules in whatever medium they're traveling through. And so basically, however easy or hard that is going to be affected by the medium because various mediums have different molecular structures and so forth. Also, it makes sense that as the temperature goes up, the speed of sound would increase because the medium would be moving more rapidly, and therefore the sound wave would be able to move more rapidly. And if you look at the table here, one example, look here at the difference air at 32 degrees versus air at 68 degrees, you can see that there's a modest increase in sound velocity. If you look at fresh water at 32 versus 68, again, an increase in velocity. And now notice, if you compare air at 32 to water at 32, the velocity of sound is 4 times as fast in water compared to air. Air's molecules are much farther apart than water's molecules. But then you get really close together, for example, steel or aluminum, and look at the velocity in steel or aluminum. It's exceedingly fast. And so the two things here, as it says, the two things that affect the speed of sound are the temperature and the medium. And the velocity of sound in air can be measured at its 331 meters per second plus 0.61 times whatever the temperature is in degrees centigrade. And so at 0 or 32 degrees, it's 331 meters per second squared, which translates to 1,087 feet per second squared. And so this formula can be used to calculate the velocity of sound at various temperatures. And I want to show you a couple of problems doing that. We have a sound wave produced by a clock chime 515 meters away, and it's heard at 1.6 seconds later. What is the speed of sound in the surrounding air? Okay, well, let's take a look at how we would go about doing this. First of all, we know that velocity is equal to the distance or displacement of the wave divided by the time taken to do that. And in this case, it's going to be 515 divided by 1.6. And that's going to equal 321. And let's look at our three significant figures. So actually it's 322 meters per second. So that's the velocity of sound. The sound wave has a frequency of 436. So what is the period? Well, remember that period is 1 over the frequency. So it's going to be 1 over 436. And if you take 436 and take the inverse of that, you get 0.023 seconds. So the period is 0.023 seconds. What is the wavelength? Well, remember that V, velocity, is equal to frequency times wavelength. And so wavelength is going to equal velocity divided by frequency. And so that's going to be 322 divided by 436. So 322 divided by 436 is going to equal 0.7 339 meters. And then what is the air temperature? Okay, so velocity is equal to 331 plus 0.6. Let me make sure I got the formula right. Yeah, 331 plus 0.61 times whatever the temperature is. And so our velocity is 322. 331 plus 0.61 times the temperature in degrees centigrade. And so if you subtract these two, you're going to get minus 9 is equal to 0.61 times the temperature. So if we subtract, or we take 9 minus 9, and we divide that by 0.61, so the temperature equals minus 14.8 degrees centigrade. So let's take a look at this second problem while we're here. A hiker shouts toward a vertical cliff 685 feet away. The echo is heard 4 seconds later. Now remember, the echo is the time it takes to go to the object and then come back. And so it's going to be 685 and 685 total distance traveled. So what is the speed of sound in the surrounding air? So you have to take 2 times 685 to get the total distance traveled. So that's actually 1,370 meters is the distance traveled, and it does it in 4 seconds. And so if we take that, we get 342.5 meters per second. Now this is 3 significant figures, so you could say 343. So 343 meters per second. If the wavelength is 0.75, what is the frequency? Okay, we have V is equal to F lambda, so now F is going to be V divided by lambda, or lambda, I was right the first time. So that's 343 divided by 0.75, and that's going to equal a frequency of 457 hertz. And then what is the period? The period is 1 over the frequency. And so that's going to be 1 over 457. So we take the inverse of this, and the period is 0.00219 seconds. And then lastly, what is the air temperature? We use this same equation here. V is equal to 331 plus 0.61 times the temperature. And now we have 343 is equal to 331 plus 0.61 C. So 0.61 C is going to equal 12. So if we divide 12 by 0.61, we get an air temperature of approximately 19.7 degrees centigrade. Okay, now let's talk about some other phenomenon that can occur with sound waves. And one is shown here with an airplane that travels at various speeds. And these various speeds are defined in different ways. So the first one, or the one that's most interesting, is called supersonic, and that's when something travels faster than the speed of sound, shown on the right here. Subsonic is when you're below the speed of sound, which is the second from the left. And in the middle, or the third from the left, is when it travels at the speed of sound. The shock wave is a compression wave that occurs along the border of this cone of sound that is shown here. This is a cone of sound here, and the shock wave is on the border of this cone of sound. And so this is what leads to what's called the sonic boom. A sonic boom is what occurs when this shock wave reaches the human ear. Now, bats do something called echolocation. They use sonic waves to locate things. And this sonic wave is sent out from the bat, shown in gray, strikes the bug, and then comes back, shown in another color that I don't know what it is because I'm colorblind, and he can locate that bug. Now the reflection here is a persistence of sound known as reverberation, and he's using this echo or reflection of sound in order to locate that bug. Now for an echo to actually be heard, it has the reflecting surface has to be at least 17 meters from the receptive surface, and that is a function of the speed of sound. Sonar is a mechanical system that is used to locate things using sound, and it can also determine the size, shape, and distance. And so in the Second World War, they used sonar or sound waves to locate submarines under the water in order to fight them or strike them even though they couldn't see them. And here's an example of sound waves being reflected off something off the bottom of the water, and the sound waves can then be interpreted by various instruments and can not only show you how far down it is, but also the size and the shape. Now, as it turns out, there's an interesting thing that occurs because of we've been talking about sound reflection, but sound as a wave can also be refracted. And sound waves, when they are refracted, they always bend toward a medium that slows them down. So they bend toward the medium that slows them down and away from a medium that speeds them up. Remember, decreasing temperature slows sound down, increasing temperature speeds it up. So if you play music, the air up higher up is cooler, and so it slows it down, and it bends therefore toward that, and therefore keeps it says during a nighttime, cool ground, the ground cools quickly, therefore the wave bends toward this ground and keeps the music loud at night, and it's louder at night because of this effect than during the day when the ground is warmer. Let's look at this another way. Here's a situation where you have warm air closer to the ground, say during the day when the sun is beating down on the ground, and cooler at night, and it bends toward the medium that slows it down, so it bends up toward the top. The dog can't hear the sound. But in the evening or late, when the ground gets cool, the air is warmer than the ground, it bends down toward the ground, and the dog can hear the sound. This can be used in the military by something known as a thermocline. What this is it changes in temperature depending on where the water is, and it causes sonar waves to be bent in various refractive ways. And if you find the right place, you can see there's an area, because of the temperature, this is bent up, meaning it's cooler up here than here, but bent down, meaning it's cooler down here than here. So right here, it's called a thermocline because it's warmer in this area than above or below it, and it is a place where there are no echoes, and if the submarine is in the thermocline, it cannot be detected by sonar. We'll finish up talking here by talking about the difference between absorption and insulation. Absorption is a process that dissipates the sound, and insulation is used in order to do that. Acoustics is a term that's used to talk about the study of sound.